right, that are only partially signed is basically worthless, right? And intuitively it sounds correct, right? That is, I get a path announcement, and someone in the middle didn't sign or didn't use the new protocol. So theoretically, right, anyone can lie, right, about the rest, right? And the reason that this is actually, I would say, wrong, there's two reasons. One is partially signed in general might be worthless, but there are special cases of partially signed that have a lot of value. Specifically, if the suffix is signed. What do I mean by this? I mean, if I can prove to you that this route has 4 hops, and I don't know if the last ones are actually on the route, but it's a route to Google, and I know that Google was the last hop, and I know that it did authorize this route to the organization before it. This is actually extremely valuable. This is one thing we've shown experimentally, and the reason is that internet paths are short. So if the attacker has to forge paths that are long to begin with, right, it's actually not going to get a lot of traffic. Another reason is that surprisingly, and this is an observation by others, Ethan Katz and various others, right? But surprisingly or not surprisingly, most content traverses extremely short paths. Right? So what happens to routing security when all you're trying to do is ensure that the last hop is secure? Right? So this is one observation. The other thing I want to talk about briefly is NTP, the network time protocol. Why is NTP vulnerable? 2 reasons. One is it relies on few servers, typically 4. Right? Not only that, but they're actually often DNS cached, right? So if I only talk to 4 servers, but if I talk to them tomorrow, it will be the same 4 servers. The other thing is that without going into the details of the selection algorithm, it assumes there's a trust issue there. Right? It assumes that no one is being too strategic about the process. Right? So the assumption is that the attacker is not powerful or sophisticated. So recently we presented Chronos, which is a different NTP client that basically tries to, there's very few innovative ideas in Chronos. It's basically a question of what would happen if we just used the theory of distributed computing regarding time synchronization to this context. And interestingly, people haven't, because it was developed at roughly the same time as Chronos. There are 2 parallel tracks. So what do we want? We want to rely on many NTP servers, because if I can only talk to 2, then I'm doomed. Right? So we'll create a large server pool. So think of you're somewhere in Europe. There's probably hundreds of servers that are close to you that you could potentially talk to. But you don't want to talk to all of them, because that would be like a denial of service attack on these servers. Right? So at each point in time, you would want to query a few, but query them in a clever way. What does clever mean here? Basically just uniformly at random. Right? Just let's query a few, but not be too predictable to anyone. And then the last ingredient is, let's use the standard trick in distributed computing theory to remove outliers. And what's the standard trick? If you get responses, order them, and then remove the top third and the bottom third. Intuitively, why is this a clever trick? Because if I'm the attacker, I'm faced with a horrible dilemma and there's no good answer. One option is say something extreme, but then you'll be discarded. The other is survive, but at the cost of behaving well. Right? I don't care if you're an attacker to behave well. So here's something from the paper that we analyzed. Shifting time of the Chronos client by 100 milliseconds from the universal time will take the attacker roughly 22 years in expectation, right, for choice of parameters. But that goes back to your question, I think. So if you and I adopt this, subject to assumptions about how many of the servers the attacker controls, we'll have this guarantee that we're not far from each other. And actually not being far from each other is more important than absolute time in this context, because if you're running a security protocol, I want us to agree on the time relative to each other. So the conclusion is, the internet is alarmingly insecure, but I don't think it has to be. Right? We do need to start rethinking quite a few things. Thank you. Yes.
Isn't it? So, this relates to the question whether our security is a binary thing. Right? You are binary. I mean, isn't it somehow related to the empty completeness and approximations? Can you have approximate? You define some very nice measure for security. 0 is non-secure. 1 is absolutely secure, and then you try to achieve different. Is there any theory for that, or is it just always intuitive and
There's
engineering?
some, but for example, in the distributed computing theory context, it is an approximation, but in the sense of what fraction of the nodes does the attacker need to control to do certain things.
Yeah.
So it's phrased in that. It's not an approximability issue, but it's more of a when can an attack be successful to some extent, right? As a function of the capabilities of the man in the middle.
So you can come up with theoretical models for that.
And there are, right?
I see.
I think Sharon also had a paper, SORA 2015 or 16, where she defined for routing security some notion of approximation based on your neighborhood size in the graph.
Yeah, that's right. I think there were various attempts. So some were the neighborhood size, some were how many nodes were you able to attract, whose traffic were you able to attract, right? Volumes of traffic, yeah. Yes.
So this,
Yeah, go ahead.
so very interesting. So I wonder if you can like combine detection with mitigation, so add another dimension to your thoughts.
That would be very
In
interesting.
that, can you isolate the attacks so that they are easier to mitigate, or although they may start some attacks, but their mitigation time can be much shortened.
So that's very interesting. We haven't thought along these lines yet, but it seems like if you could do that, that would be very
Yeah, I
cool.
think it's along the line of your.
Yeah.
So I have a very general question, which is to what extent the problems that routing decisions and networks are similar to consensus problems, because like in NDP case it looks like you have basically Byzantine consensus sort of that you need to resolve, though in numerical sense, not in the decision sense.
Mm-hmm.
And if we're looking at like permissionless blockchains and all that kind of business, then suddenly it becomes sort of similar, because you have the routing protocol that is permissionless, right? Because you don't have anyone to to let in. There's no way to do that. And at the same time, you still want to provide certain properties that would agree upon between the players. So to what extent these things do
So I
things
think in some, as you said actually, in some cases extremely close, like the NTP context, where it's essentially exactly what you said, it's consensus, right? In others, quite far, because for example, in the routing context, the issue isn't that there's ground truth that's decentralized across the different entities. It's the issue of how do I even bootstrap the ground truth, right? So blockchains arise once you can bootstrap the truth to begin with, right? Because the system somehow needs to know that I have 3 Bitcoins initially, right? I can do something with. But here, a lot of the issues is that you're starting with a very vague situation. It's not clear how to verify anything to begin with. But it's, I know that people have thought along the lines of utilizing blockchains for these purposes, but we have yet to see, I think, the killer app.
Yeah, that is true for
Of
blockchain in
blockchains.
general.
Right, of blockchains. That wasn't about routing security.
Right. I think for something like getting the time, you need an interactive protocol. I mean, just because you said that you can't allow the bad guy to save a signed state
Right.
and give it to you later, but you could boot up with nothing other than a random number generator and generate a nonce and send it to someone whose public key you trust, like someone.
In which
Yeah.
context? The time
In
context?
the time context, and if they give you a reply within 5 seconds that signs both the nonce and some statement about the time, you have the time within 5 seconds.
Good.
As long as it's interactive.
Yeah, I mean, there's a trade-off obviously between the level of precision and accuracy you want, right? If it's 1 millisecond or 5 seconds, right? Which for some applications, 5 seconds might be more than enough.
Yeah, I don't know a lot of internet cryptographic applications where knowing the time is better than the absolute time is better than a minute is particularly important.
So I know that there are examples of a second. I'm not sure if there is. I need to reconstruct the
Well, there are examples of cryptographic, you need the certificate to be valid, and if your, certificate time is short, then and the time is off, then you will, then the certificate will be kind of timed off or some way
Sure,
invalidated.
but you really need better than a minute. I mean, typically the certificate lasts like 3 months, and it's renewed once a month or something like that.
I could imagine that one time, one time-based authentication protocol would rely on something like second or so granularity.
Also, if you think about all those scanner things, right? Wouldn't they be somehow dependent on that? No, they don't use NTP. They use GPS, but that's the reason why they use GPS and not NTP.
Yeah, but what is the NTP? It's good for which accuracy in compared to PTT, because PTT is more.
It should be more like microseconds, but it's something different.
It's not.
It's not. Most chances are that your smartphone is running NTP.
So, I think in the spanner case, what's important for true time is to know the clock accuracy. So I think if you send a request with a particular nonce,
Right.
you know that you can bound how long a bad guy could have delayed it.
Mhm.
But I think the spanner guarantee is still there, though of course it's better to have a more accurate clock.
So both the solutions you sort of talked about seem like making it more expensive for the attacker. So like one way to look at it is your NTP argument was I have 100 people, and some of the BGP argument was I have one hop. So I wonder, like, is the response then just let's replace the internet algorithm, internet protocols with ones which require more expensive attackers? So for example, like why Chronos? Why don't we just go to GPS receiver? Like my phone has GPS. Why is my phone relying on the NTP synchronization period anyways? And like I guess my laptop doesn't yet, but would it really be that expensive to?
So that's a good question. I don't know what the NTP. Yeah.
Well, you know what the answer is? The recent evaluation of GPS spoofing impact, or 30 days of GPS spoofing on US industry, is that it would be 1 billion per day wasted because of GPS spoofing. So GPS is this another link that you cannot possibly rely upon, and everyone relies upon, right? So it's like your BGP example.
So I guess it is expensive.
I guess.
But I don't know.
I guess my question is like to Keith's point, like suppose I say, okay, this is, I know this is like, I'm not defending myself on the security of it. I'm going to get the US government to launch 100 satellites with whose public keys they are publicly distributed to everyone, and that's my solution for avoiding GPS spoofing at the moment.
But I think it needs to be interactive, where you have this hold on to it later.
No, because I'm going to really only receive it on the GPS link. Like you'd have, like I want to receive, like surely. Okay.
You can spoof GPS somewhere to the ground. You don't need a satellite to spoof GPS.
So I'm abusing power here because I load the speaker and you
No.
So I will tell myself that we'll continue taking questions offline.